Up until now, we've looked at the concept of system design and considered the connection to ground is a perfect connection. It's got 0 ohms, it's got no resistance whatsoever, and it doesn't cause us any problems. But in reality, ground and the definition of ground in circuits is actually a very complex problem. In this lecture, we're going to look at the issues of ground and how we can actually compensate for ground and make sure that our circuits accurately reflect the signals we want and don't give us errors due to things like ground. So the first thing to say is there is no ground. There is no concept of ground in electronics. If we look at this very simple circuit on the front of this book, the power flows from the battery to the switch, it flows through the coil, and it flows back to the battery. It doesn't flow away into a magic ground puddle. There is only 2 connections for electricity, and signals only flow over 2 wires. Up until all your studies so far have assumed that connections between them components are ideal. In other words, there is no resistance. All the wires that we draw are all perfect connections. But that's not reality. All cables and all wires have got resistance, and they have a significant both resistance and impedance. Let's have a quick look at calculating the resistance of a circuit board track, a printed circuit board. So here we have a piece of copper sitting on top of a circuit board, and we're going to assume that it's about just over 0.5 millimeter wide, about 630 microns. We're going to assume that it's a standard production run from circuit boards, so it'll be about 35 micrometers thick, and it's running across a typical sized circuit board, so we're going to say it's about 160 millimeters long. So let's calculate out the resistance from one end to the other. Looking up the tables, the resistance of copper is about 1.7 micro centimeters. We can work out the resistance here is equivalent to about 0.1 of an ohm. Now you all may say 0.1 of an ohm, that's a tiny resistance, so that'll not cause any problems whatsoever. Let's have an analysis of a typical circuit, one that you've seen before, and let's look at how big a problem. If we have some signal wires with resistances of say 0.1 ohms, and we have some typical signal currents of perhaps 10 volts going into a 10k ohm load, such as this amplifier here, then that'll give us a current of about 1 milliamp. 1 milliamp into 100 milliohms gives us about 100 microvolts. That's actually a significant error when we're looking at things like thermocouples. So let's look at a real circuit board's layout here. So we've got our thermocouple connected in this fashion here, and this is a typical board that you may find inside an instrument or a piece of equipment or even inside your laptop computers. We've got a load current which is flowing out onto the 10k ohm load, and the load current has necessarily got to return from the load all the way back to the 0 volt terminal on the power supply. But because it has to flow through a PCB track, there is a voltage drop here. That is generating an error. So let's look at what you've really built. Not what you drew in the schematic, but let's look at what you've really actually built. You've actually placed a 0.1 ohm resistor in series between the load and the 0 volt terminal on the 15 volt supply rail. It's generating 120 microvolts across that because of the current. So we now have a gain change in our circuit here, which is actually causing about a 2 centigrade error for a typical K-type thermocouple. We have an error that is proportional to the load current. That's not what we designed. How can we remove it? We've only considered one amplifier here with one thermocouple, but imagine you had many amplifiers with many thermocouples, and they're connected up in this fashion here. So you have amplifier 1 here, which is passing 1 milliamp through 10 ohms into your resistance. You've got a second amplifier here, which is passing a further milliamp into the resistance, and a third amplifier here. So rapidly, the errors due to the load currents is actually getting quite complex. And it all comes down to the detailed design of your circuit board. To actually design this product sensibly is almost impossible by using the configuration that we've shown here. How can we improve it? But you may say, oh well, in logic things are much easier. Well, actually they're not. In logic, life is a lot harder, because fast logic actually generates very large spikes. So let's do the analysis, and let's take a simple CMOS NOT gate, an inverter. This is what it looks like. We have an input terminal, we've got a plus 5 volt rail, and we have an output terminal. And what we have here is we have current supply, and we've got an output voltage. When the input is low and the output is high, this top device here is turned on, and the output voltage gives us an output 1. And the current flow is actually quite small in this mode because there is only one transistor here, the top one is on and the bottom one is off. However, as the input voltage starts to rise, then what happens is the bottom transistor begins to turn on, and we start seeing that the supply current increases due to the bottom transistor turning on a little, but the top transistor is not yet turned off. So we actually have conduction through the top transistor and the bottom transistor here. When the input actually goes to a hard 1, then it turns off the top transistor and only the bottom transistor conducts. So we have a spike here as both transistors turn on, and then a reduction in current when the top transistor turns off. So we end up with very large current spikes in digital circuits. So let's work out and try to understand some typical values of what we call ground bounce. This is the current that's flowing into the ground during the switching time. We can work out the charge that a switch actually generates, which is the time it takes for a switch, times the maximum current, and we can work it out from this equation here. So let's apply some simple numbers. And we'll also define a power dissipation capacitance. And the power dissipation capacitance is the switching charge divided by the voltage, which is roughly equivalent to the switching time divided by the switching resistance. Let's take a very typical logic gate. It's an 74AHC00, which is a bunch of 4 NAND gates, I think it is. We're going to define a power dissipation capacitance of 9 picofarads, a time for switching of 3.5 nanoseconds, which is relatively slow. It's only about 300 megahertz. And the current spike, we're going to say, is Imax is 13 milliamps. In other words, a single gate flowing into a 0.12 ohm resistance, such as we have on this PCB track, could give us a pulse of 1.6 millivolts. However, if we assume that there's some inductance in the track, and let's assume the inductance is about 0.2 microhenries, that is equivalent to about 32 ohms as impedance. So times the speed of the pulse, we now get 0.42 volts of a current spike. A large digital system can produce up to 1 volt of just ground bounce junk, and it's very difficult to control this. Thank you very much. And we're now going to go on to look at how we can control ground bounce in these events.